All right, everyone, let's get started. Okay, let me just make sure this is okay. All right, so today we're going to be discussing attention mechanisms. So if you remember from last class, we went through gradient descent, we went through backprop, and at the end of the class, we talked about recurrent neural networks. We went through the backprop through time, and we've already talked about how recurrent neural language models have several advantages over the other variants that we've seen to this point, right? We've seen n-gram models, we've seen fixed window language models, but recurrent neural networks also have some downsides. And so in this lecture, we'll be talking about the attention mechanism as first a way to kind of alleviate some of the issues with recurrent neural networks, and then later how attention mechanisms can be removed from recurrent neural networks and built into its own architecture called the transformer. So this class will be focusing on attention and self-attention. In the next class, we'll talk about how you can put all of the things we've learned together to get the transformer model, which then we'll talk about for a while longer. All right, so before we get into it, some logistics stuff. So the homework 0 grading will start this week and hopefully be done by next week. So you'll see all your grades in GradeScope. All project group assignments are finalized now. There might be a few changes here and there because people added and dropped and so on, and you'll get notified if someone is added or dropped from your group. But it should be like 99% done right now. So this week, hopefully all of you can coordinate with your group members and get started on brainstorming project ideas and eventually writing them up into your proposal. Please go to our office hours if you want any feedback at all before the proposal. There's a sample proposal paired with some feedback in Piazza that you can take a look at. There's also in Piazza a example final report, which you can look at to see, which report got the highest grade, like 2 years ago or something. I also noticed there's a lot of old midterms in the Piazza resources section. I guess it copied them over from last semester, so feel free to look at those, although we're still quite far away from the midterm. You will have a homework 1 released after the project proposal deadline. So that homework it'll require you to link up with someone in your final project group or someone else in the class and get them to annotate a data set for you, and then you will train a model on this new little data set that you've created. So it'll get you some experience using the Hugging Face library, using Google Colab to train models and so on. So a couple of you have asked about compute resources for projects. This semester, so we've used Google Colab for basically everything for the last 3 years. This semester, it looks like Google Colab may be less reliable than usual as Google is trying to monetize this product now. So one of the TAs is putting together some alternatives for your final projects that you can take a look at. There are some paid alternatives, so like Google Colab Pro could be worthwhile for some of you if you're intent on doing training of larger models. It's like $10 a month, which is pretty reasonable divided amongst your group. There's also some potential for Google Cloud credits. So I've applied for some credits for the whole class, but I'll have to wait to see what they say. So one of the TAs will write up a Piazza post with all these different alternatives that hopefully will come in handy for the rest of the semester. Okay, any questions, admin or project related? All right, let's move forward then. So this slide we saw a couple lectures ago. It's the recurrent neural network language model. And so remember that in an RNN, the computation proceeds left to right. So it's as if the model is receiving one new word at every time step and updating its representation of what it's seen in the past based on this new word. And we went through the backprop, or at least partially went through it, for the case where these are single scalars and these matrices are also single scalars. The intuition is basically the same. You're still going to do backpropagation through time. It's just that the actual computations are not just scalar multiplications, but matrix vector products and so on. Okay, so we briefly talked about the advantages and disadvantages, right? So advantages of the RNN are it can theoretically at least process any variable length input sequence, and the model size is not dependent on the length of the input sequence. Furthermore, the weights that are used to process each word are the same at every time step. So some of the disadvantages, which we'll be looking at specifically in this class, are that first, the recurrent computation is slow. So I cannot compute h sub 4 without first having computed h sub 3, and h sub 2, and h sub 1, and h sub 0, right? So there's no way for me to parallelize the computations of all of these time steps because they depend on one another. As we'll see, this is a big bottleneck during training these models, especially for very long sequences, and we'll be moving towards a model where you can compute all of these h's in parallel because there are no dependencies between them. Another practical issue with the RNN is that it's difficult for the model to access and make use of information that occurred many time steps in the past. So although theoretically the model can handle some arbitrarily long sequence, in practice that's not the case. And so we might want a way for the model to have some sort of shortcut connections to faraway states that doesn't depend on the recurrent computation. We also discussed a related problem, the vanishing gradient problem, where contributions from very far away time steps may not actually influence the model during training. Okay, so before we get into the topic of today, let's just kind of synthesize the concepts that we learned from the previous lecture into how exactly you train a recurrent neural language model. So we know all the pieces of doing this, right? First, we collect some training data set, which is just text. And maybe each training example in your corpus is a sequence. So it could be like a sentence, it could be a document, a paragraph, whatever. It's a sequence of words. So you're going to feed the sequence of words, each sequence, into an RNN, right? So each word in the sequence represents one time step in the RNN. And at every time step, you're going to predict a probability distribution over the next word, right? So this is going to be conditioned on all of the tokens you've observed to this point. So to make it more clear, let's say we have our input sequence, the students open there. And we're trying, the fifth word here is exams. But in an RNN language model, we're going to be making a prediction at every time step of the network, not just the last time step. So given h sub 1, we're going to pass this through our softmax layer, and we're going to compute the cross entropy loss where the ground truth is the next word here, students, right? So at h sub 1, the model has only seen the word the. It's not seen the word students. And so we can make the model predict the next word from this, this representation h sub 1. So we get one loss term here, which corresponds to how well did the model do given h sub 1 at predicting the word students, right? We already saw how to do this using the cross entropy loss. Next, after we compute that loss, we're going to move to the next time step, h sub 2. Now the model has seen the students, and so its target is the next word opened, right? So when we compute h sub 2, we're going to go through our softmax layer, get a distribution, and then compare it to the ground truth distribution, which has 100% probability on opened and 0% probability on every other word in the vocabulary, right? And if you notice here, the word that we're trying to predict is actually in the sequence that we have, our training sequence, right? It's just that the model at every time step, because of the recurrent computation, it only sees all the words up to and including this particular word at this time step. So h sub 3 sees the students open there. It has no information about the word there. So it is valid to use this representation to predict the word there, right? So similarly, I can compute this loss at every single time step of predicting the ground truth next word. I can take the mean of all of these losses, the mean across the sequence, and that becomes the loss that I eventually backprop into. So if you're interested, you can set up an example just like the one we did in the last class with the RNN, where the loss is not at the end, over the last hidden state of the RNN, but actually at every single time step. And you can see how, I mean, it's not that hard to see how you can backprop the loss at every time step. It's just that the loss at time step 3 does not affect the backprop when you're at time step 4, right? Okay, so, and remember how we actually compute the loss, right? It's the cross entropy loss using the predicted probability distribution, the output of our softmax layer, and the ground truth probability distribution with 100% probability mass on the correct word. And so we average this, we get the overall loss on the training set, and then we backpropagate and adjust our model parameters. All right, any questions about that?
Can you tell us something more about the initial hidden state that gets passed?
Oh, this thing?
Yeah, and how would it affect the entire, like any changes to the initialization of that vector, how would it affect?
Yeah, so the question is about this initial hidden state and how changing it could affect the behavior of the network. Generally, this initial hidden state is treated as a learned parameter. So note that h1, h2, h3, h4, those are all intermediate variables, right? Hidden states that are products of the other parameters. H sub 0 is it's not the product of any computation, right? So we can either treat it as a parameter, just like our C sub i's, our word embeddings, or we can just treat it as like, we can initialize it to all zeros and keep it fixed. We can initialize to some random value and keep it fixed. In general, people usually just learn this as a different parameter. But yeah, of course it has some impact on what's happening here. But as long as the model knows how to deal with whatever the initial hidden state is, it should be fine. And this is the same for every single sequence, this initial hidden state, right? So as long as the model is trained with one of these, either this being zeros or this being a learned parameter, it should work fine. Yes?
What is the significance of calculating the intermediate loss?
The question is, what is the significance of calculating the intermediate loss values? So, okay, imagine if I only calculated the loss at time step 4. That would be like, you wouldn't have to compute any of these previous losses. The issue with that is this only gives you the prediction of the word exams, right? And you have a full sequence of many, many tokens. Each prefix of the sequence can be used as an input example for language modeling, right? So given the students, I might want to predict open. Given the students opened, I might want to predict there. And so the point of having all of these losses at each token is that you can efficiently compute all of these losses with one left to right processing of the sequence, rather than if you didn't do this, then you'd have to put in like the sequence the students and then use the last time step to predict opened. Then you'd have to put in a new sequence, the students opened, and predict the next word. But this is a complete waste, right? Because you already have all these hidden states. So why not just do the prediction sequentially as well? That's the general idea. So it's much more efficient to do it like this and have these losses at every time step than it is to split this input sequence into multiple prefixes like the students open, process all of them separately. Does that make sense?
So we do this, the main reason of why we do this is for the efficiency or the accuracy?
Those two, so the question is, do you do this for efficiency, this being having these token level losses, or do you do it for accuracy? So accuracy-wise, both methods are the same computations are happening. We're doing this solely for efficiency because there's no reason not to, right? If I've already computed the representation for the students, why would I recompute that if I wanted to, compute the representation for the students opened? The RNN gives me this natural left to right progression, so I should take advantage of that.
So then there's one Minibatch of examples that you train on, take many sentences that then each have several different losses in them, so you take the batch over.
Yes. Okay. So the question is about how a mini batch works in this setup. So a mini batch in this setup is composed of multiple different sequences. So you could have, the students open their exams as one example. You could have they looked at the first problem and became sad. That's the next example. I could have all these sequences, right? And in each sequence, for every single token, I'm going to have a loss, which corresponds to predicting the next word of that sequence. So I'm going to have a matrix of losses, each for the next word of that particular location in the sequence. I'm going to take the mean over all of those, the entire batch, and then use that as my loss.
Instead of finding out loss for every given state, what if we try to do for every 2 hidden states, because it will be less computational?
So the question is, instead of computing this loss at every time step, why don't we compute it at every other time step? Wouldn't that save compute? It actually doesn't really save you any compute if you do that. So the reason is, if you wanted to compute the loss at j sub 1 and j sub 3, at time step 1 and time step 3, you still have to compute everything, the representation for time step 2, right? Because otherwise, without this, you can't compute time step 3. So you're not saving anything other than possibly something at this output layer. But we can talk about that if you're more interested. The implementation-wise, it is nowhere near, it saves you basically nothing to do this. Yes?
Professor, over here, when we take the average of the losses across the board, we are considering same weight for the first case where you're predicting only with one prefix, and you're considering the same weight when you're predicting 4 prefix. So is that like the optimal case? Or
oh, I see. So the question is, all 4 of these predictions are treated equally under this, because we're averaging them using a uniform average. Perhaps you could use a weighted average where some token predictions are more important than others in this loss. Yeah, you could try doing stuff like this, but I think people have experimented with this, and in general, it doesn't really affect things. It's always hard when you introduce weights into the loss function to get it to behave the way you want to. So that's probably one reason. But another is that it doesn't seem to be necessary, in fact, to apply. But that's a good question. All right. Yeah.
Do we update the weights at every step?
Oh, the question is, do we update these weights, WH and WE, at every time step? Or do we update the weights after computing all of the losses for a batch? So the answer is the latter. You compute, you don't do the update until you finish processing all the sequences in one batch. You compute the mean loss, and then you backprop into those. Yeah.
So coming back to the question that
You cannot just weight the losses, right? Because it's like the whole sequence that you're modeling. So basically, it's like the multiplication of all the probabilities, all the conditional probabilities. That's the probability of the whole sequence is basically, if you factor them out, it's basically the multiplication of all the probabilities, and then you're like taking the log and maximizing the log size.
No, I mean, you can certainly add any weight that you want to each of these loss terms. It doesn't affect it will just affect what, I mean, that weight will be back propagated into the network and influence the size of the gradient update. So maybe you can think about that a little more and see if it makes sense. All right, last question. That's a good question. So in one mini batch, are all of the sequences of the same length? In general, so there are many techniques to deal with this. One is if you have a huge data set, you might sort all the sentences by length and then select and kind of make buckets such that each batch consists of sentences of roughly the same length. Of course, this might not always be feasible. So the other solution is to add padding to some of the shorter sentences in the batch. So you have a special pad token that you add to the end of this model, and you don't compute, you add to the end of these short sequences. You don't compute a loss for the pad tokens. But you want to minimize the amount of padding that you add to any batch because it's just wasted computation. So yeah, okay, really last question.
It makes sense, but what's the point of having sentences be the same length in the batch if we're going to be averaging one loss?
Right, so the question is, what's the point of having the sentence be the same length in the batch? This will make more sense when we actually talk about how these things are implemented. But basically, you compute the first hidden state for every single example in the batch, and only then do you proceed to computing the second hidden state for every. So you're not doing like one sequence and then the next sequence and then the next sequence. You're doing all the time steps in parallel across the batch. So that means that if some of the sentences are super long and others are short, you're just wasting computation for those shorter sentences because there's no information there for those later time steps. That'll make more sense when we go through an implementation. All right, let me proceed here. So one of the biggest issues with recurrent neural networks is that they suffer from a bottleneck problem, which becomes more apparent as the sequences get longer and longer. The bottleneck refers to the fact that the current hidden state, h sub t, at time step t, it has to encode all of the information about the entire prefix that it's seen up till that point. Right? So here, h sub 4 is supposed to represent the prefix the students opened there. And you only have one vector representing this prefix. So if this sequence was not just 4 words, but say 1,000 words long, now you're squeezing all this information into a single vector, and the result is that a lot of important information could be lost during this process. So there's this now famous quote by a famous NLP professor, Ray Mooney: "You can't cram the meaning of a whole bleeping sentence into a single bleeping vector." And now, if we're dealing with much, much longer sequences, this becomes even more implausible that you can do this. So what is the alternative? The idea behind the attention mechanism is that you give the model a way to get out of this bottleneck state by looking at previous hidden states as well. So given the students open there, in the current RNN that we've seen to this point, this last time step contains all the information about the students open there. The model will just feed this into the softmax layer and predict the next word. But what if we represent this prefix with all 4 of the hidden states that we've computed up until this point? And so now, before going to the softmax layer, the model is able to do a linear combination of all 4 of these vectors based on which ones it thinks are most important to predicting the next word at this particular time step. So it's able to actually decide decide which vector to place most of its attention over, and then it's going to predict the next word. So that's generally the idea. So one of your readings was the original paper that introduced the concept of attention, which was within this recurrent neural network setup, specifically to improve machine translation. So we'll have a whole lecture about machine translation in the future. But essentially, this allows a language model to look not only at just the last time step, but also at any previous time steps. And if some of those are more important than the last time step in making this prediction, then this model can, the attention mechanism can theoretically help. All right, so how does it work? At a high level, when we want to compute attention, we have a single query vector, and we're going to use this query vector to compute scores over a bunch of different keys. So in our language model setup, I'll just go ahead and answer this question in the yellow. We might have the case that our current hidden state, h sub t, is used as a query vector, and all of the previous hidden states are used as key vectors. And so this is one way to look at it. We'll see later in this class another way where you actually perform some projections of your word embeddings and use those as keys and queries, but that's a little bit in the future. So let's just go through how this might work in an RNN language model to give you some intuition. Okay, so let's say we have observed the students open their books. And so this word books here, we've computed this hidden state, h sub 5, I guess, or 4, or whatever. And this is going to be our query representation. So now, each of the previous hidden states, we're going to consider as keys. And our goal is to score words here that we think are most informative to making the prediction of the next word. We want those scores to be higher, and we want other words that maybe are not relevant in this context or not as relevant to be scored lower. So one easy way to get these scores, so we want some scalar scores, is to just take the dot product between this query vector and all 4 of these key vectors, right? So we get these 4 numbers. These are called the attention scores. But these numbers could be, negative. They could be have a big range and so on. And we've already learned about this softmax function, which we can use to turn any vector into a probability distribution. So in the attention mechanism, we're going to first take the dot product or compute some similarity score, and then we're going to apply the softmax function over the attention scores, so we get a distribution over the keys, a probability distribution. So here, it looks like this model has, for some reason, it thinks that this first hidden state is very important to making the next prediction, and that none of these are very useful. This is just a random example. The attention scores may not look like this at all. So given this attention distribution, what we do then is use these probabilities as weights to compute a weighted average of the key vectors, which in this case are the previous time steps. So I'm going to multiply this probability by this vector, add it to this probability times this vector, and so take the weighted average of all these 4 vectors, and eventually I get this final vector, which is the weighted average of all of our keys where the weights come from these attention scores. Does that make sense? And so now I have my current time step representation, h sub 4. I also have this attention vector, which now has information about that the model thinks is relevant from the entire previous hidden states, right? So this vector here, it looks like it contains information mostly from the very first time step. So what we're going to do is take this vector and concatenate it or compose it using some other method with our current hidden state, and then feed the result into the softmax layer. So Here, we're going to apply concatenation, say, so we get this red vector concatenated with this green vector. Then we feed that through a softmax layer and get a probability distribution over the next word. Now, when we have the next word, there should be an arrow between unwillingly and books. So now this previous hidden state, H sub 4, now becomes a key when we're computing the attention distribution over for the next time step. So you can see here that now this current hidden state is no longer, it doesn't have to be a bottleneck anymore, right? Because we also have these attention scores which allow us to look back in potentially very far back in the input context, depending on what score the attention, what attention score is assigned to that time step. All right, so what does this actually allow us to do? Well, like I just said, it allows us to solve this bottleneck problem. So now we have these kind of shortcut connections to faraway time steps. The last bullet here, attention provides some interpretability, is it's a little questionable. So it's kind of true in simple networks for tasks like machine translation, where you can look at word alignment and see from the attention scores, you know, that this word in English is has a high attention score with the same word in French. But in general, when you stack these attention-based layers on top of each other and make a very big network, it becomes impossible to interpret what the attention actually means. So there are many papers that we'll look at some of them later on in this class in the semester about how attention is either interpretable, it's not interpretable. There's a paper like it's not interpretable. I don't know what that is referring to, but we'll talk about all of those things later on. Yes.
So if we're using hidden states from previous tokens in the sequence, I'm confused how are you able to predict new words from that rather than like at first look it looks like we're looking at which words in the previous sequence to predict as the next one rather than predicting a new word from this.
So our current time step here has information about the students open their books. The attention output is over these keys, right, which are all the words that precede this current word. And our goal is to predict the next word. So we're hoping that this attention will give us more useful information about what occurred well in the past that could be helpful in predicting the next word. So maybe, you know, there was some description of the students being grumpy before, and the attention was able to focus on that. And this vector then becomes very useful in predicting the next word.
Okay, so each hidden state has equal weight when predicting the next token instead of
so each hidden state does not have equal weight, right? The weights are determined by this dot product between the query vector and the key vector, followed by the softmax. So like these hidden states here, they got very low probability, while this one got a very high probability. So it's being used more in the prediction of the next word.
Right. What I mean is that there's no vanishing gradient now because.
Yeah, that's right. So your comment was there's no vanishing gradient now because all of these hidden states kind of get an equal opportunity to have a large probability in this attention output. In practice, this may not be true. In practice, the network could learn to just favor close by time steps, but yeah, theoretically, this definitely helps. Okay, 2 more questions.
Why is the dot product two different hidden states that might be related show that they're related? Like we expect the hidden states to behave like we're expecting, or if they're close to each other.
So the question is, why are we computing the dot product, and why do we expect that to be a meaningful measure of similarity? I mean, so we are actually training this whole network, right? So basically, the network is going to learn, if the network learns that this dot product should be high because it results in a better prediction of the next word, then, the dot product it becomes meaningful through the training of the network. But people have explored many different similarity functions for attention, not just the dot product. We'll see a lot of those later on in this slide deck. Somewhat, yeah.
When we are doing the back propagation, do we distribute the gradient in the ratio of the attention score?
Okay, so the question is about backprop through attention. So now it's getting a little trickier, right? Because at every time step, I need to now do backprop through all of these time steps using the attention weights. Yeah, so the gradient is modulated by the attention weight at each time step for whatever previous time step you're looking at. This is one case where you probably are thrilled to not have to implement the gradient by yourself, because especially when you stack up these layers, it becomes really hard to keep track of everything. All right, I see some YouTube comments. The key vectors, because they are interim hidden states, aren't just a function of a single word, but the words up to that point. True? Yes, that's correct. So in the remainder of this class, we will look at a case where the key vectors are not, they're not hidden states, but they're rather just functions of the word embedding. Do we calculate attention vector at every hidden state or just the final hidden state? In this kind of model, we calculate the attention at every time step. So every time step, we calculate a new attention distribution. We concatenate it, the weighted average with our current hidden state, pass it through the softmax, and predict the next word. All right. So, here's the slide that maybe helps your question. So that it's not just the dot product that's useful here. The original formulation in the reading was actually more complicated. It was first you concatenate, then you do a feed forward layer, then you do some multiplication with some vector, and then you get a score. There's also bilinear product. But the most popular is the dot product and the simple scale dot product, which is used in the transformer. Again, like the meaningfulness of the similarity metric is just it's made meaningful by backpropagation. So whatever the model thinks is going to help it the most in predicting the next word is going to be learned. iPad, okay. All right, so now I want to switch gears a little, and okay. Oh, everyone gets to see my code. All right, so let's talk about one of the most important concepts that we'll learn in this class, which is called self-attention. So our goal with this part of the class is to try and get away from the recurrent neural network, which requires us to compute each hidden state sequentially. So as we discussed, that's very slow, and we would like to compute everything in parallel. That's our goal. So let's make this more clear. Motivation, get rid of recurrent computation. So let's say I have my standard example here. I have students opened there, and in the recurrent neural network, I have some initial hidden state. I have this thing, and it's not going to write out all the equations again. But right, I have my H0, H1, H2, H3. And the thing that's making this slow is these recurrent connections, where I cannot compute H3 until I compute H2. So if I can get rid of rect connections, recurrent connections, I can compute all h's in parallel. So what might this look like? If we look at where we're eventually trying to go, let me see if I can copy this. I have this thing. I want to get rid of these recurrent connections. And I want something that's more like this, where H2 is a function of students in open, H3 is a function of students open there. And if I can get to this point, then I can compute these things in parallel. Hopefully I can be fairly efficient about how I do this too. So we're going to see how we can kind of boil this down into a combination of attention and a couple matrix multiplications to do basically all the computations of these h's in parallel. That'll be our goal for the rest of this lecture. So we'll start by, how do I do this? I'll start from the bottom, I guess. Where does this begin? Okay, so let's give ourselves some space. I have students. This is my C1. Opened. There. So C1, C2, C3. And in self-attention, which is going to be the key building block of the transformer, we need something to be our query, and we need something to be our key. We also are going to introduce a new concept called a value, which is going to be used only at the end when we do our weighted average. So I'll, at the end of the lecture, relate this formulation back to what we just looked at with the recurrent neural network. But let's just follow along for now. I'm going to have three different projections here. So I'm just going to draw these and then copy it. Oops. Okay. So at every time step, I'm first going to do three projections. So this is going to be called Q1. This is the first query representation. This is going to be K1 for the key representation, V1 for the value representation. So similarly, I'm going to have all of these. And so how exactly do I compute Q1 or K1? Say Q1, actually maybe I'll use the color for Q. Q1 equals F of WQC1. Similarly, Q2 equals F of WQC2. K1, maybe make this clear. K1 equals F of WKC1. And finally, oops, I used the wrong color. My bad. And K1 equals F of WKC1. So I have three weight matrices here, WQ, WK, WV. These are linear layers, feed-forward layers, that are used to project the input word embedding into three different spaces: query space, key space, and value space. And I'm going to use these query, key, and value representations now to perform attention over this sequence. So let's start with time step 3 here. Actually, time step is a little confusing. Let's start with the third position of this sequence. So that's students open there, and I'm trying to predict the word books, right? This is our standard case. So what I'm going to do is take the dot product of Q3 with K3, Q3 with K2, and Q3 with K1. So I get 3 scores now. So I have Q3 K1, Q3 K2, and Q3 K3. And again, just like in attention, now that I've computed these query key scores, I'm going to apply the softmax function to get a distribution over the time steps. So note that in this formulation, the current position is also included as a key. Remember, in the recurrent neural network, the current hidden state was used as a query, and all preceding hidden states were keys. In this case, the current hidden state, sorry, there's no hidden state. The current query vector is, you're scoring the current key vector as well. So this could mean that the current position, C3, is not as important as C1 here, because we have a different representation for the query and key vector. So in the RNN, the query and key vectors were both the hidden states computed by the RNN. Here, there are different projections. So we have a query vector and a key vector for every single time step. And this model could learn that K1 was the most important out of all of the time step. Sorry, I keep saying time step. All of the positions in this sequence. So anyway, I apply the softmax here, and I get a distribution over the positions. So this is Q3, K1, Q3, K2, Q3, K3, and maybe it put 30% on the first time step, 50% on the second time step, and 20% on the third time step. So I have my attention distribution. And now, this is the other difference between what we saw with the RNN. So once we got this distribution in the RNN, we used it to compute the weighted average of the previous hidden states. So those were also the key vectors. You can see that in the RNN formulation, query, key, and value were all just the hidden states from the model. Here, we've actually separated these things out. So this final weighted average that we're going to do using these using these attention scores, these are going to be done on the value vectors, which is this last projection here. So I'm going to multiply, if I want to compute, say, this H3 here, now H3 equals 0.3 times V1 plus 0.5 times V2 plus 0.2 times V3. So this will give me some vector which I can use to predict the next word, predict books, through a softmax layer. So you can see that in this process, I have no recurrent update equation or anything like that. I've just done these 3 projections. I've computed attention. I've computed this weighted average of these value vectors, and that gets fed into the input into my softmax layer, right? So this was the 3rd time step here. Now let's take a look at the 2nd time step. So we're going to work our way backwards, and then we're going to see how we can actually compute all of these final vectors here, the weighted average of the value vectors, in parallel. So to do this, I suppose I will copy all of these. To a new page. Okay. So now, and maybe I'll label this with self attention at 3rd position of sequence. This will be self attention at 2nd position of sequence. So here, my goal is to compute a representation of the prefix students opened and then predict the word there. So in doing so, I don't want to use any information about this time step, right? Sorry, this position, because it already has the word that I'm trying to predict in it. So I can only use these previous two time step positions to compute the attention weighted average. So what I'm going to do here is I'm going to compute the dot product between Q2 and K2 and Q2 and K1. So now I form this vector Q2, K1, Q2, K2. I take the softmax of this, and if I plot this out, now I have Q2, K1, Q2, K2, and Q2, K3. So Q2, K3 has to be 0. I can't look at that. Someone tell me why I can't look at that, just to make sure it's clear. Exactly. So this is cheating. If I look at K3 or V3, this should be 3. If I look at K3 or V3, that's cheating, because that representation is a direct function of the word embedding at position 3 of the sequence, which is there. This is exactly what we're trying to predict at position 2. So if I include anything related to this in my computation at position 2, the model is not going to have to learn anything about the prefix in order to make the prediction of the next word. So it's cheating, as you say. If you don't understand that, you should go back and make sure you understand why you can't look at future time steps when predicting the next word, because we'll be talking about this over and over again. Okay, so here, maybe the probability was like 0.7. This one was 0.3. This is 0, obviously. So again, no Q2, K3 because of cheating. I will highlight this. Okay, so now we're going to take the weighted average of the relevant value vectors, right? So H2 equals 0.7 times V1. This is an element-wise product, 0.7 times V1 plus 0.3 times V2. So then we get this weighted average of the two value vectors, which we're going to use to predict the word, what is the word? There. Okay, is that clear? We haven't done anything fancy to this point. Yeah.
Do we need to take into account the positions of the words in the word embedding?
Yeah, so we will talk about that in the next class. That's a good question. So the question is, do we need to take into account the positions of the words in the sequence? Right now, I haven't told you about how we do that, but yes, we will talk about that in the next class. Yes.
What is the significance of naming these vectors query? In the previous example, we were having the current vector, we had query, and we could figure out the previous inherit states as.
Yeah, so the question is, what is the significance of the names query, key, and value? Query and key are fairly apparent in any sort of retrieval context, right? So you can look at this as, at the current position, I have a query representation, which maybe comes from the word at the current position. I want to use it to find the most helpful words out of the set of all words that occurred previously. You can think of it like that. And so in retrieval, whatever you're retrieving over generally called keys. Here, we additionally have this difference between the key and the value, which is more confusing to explain. In fact, there have been papers that show you can completely drop the value representations here and just use the keys as the values as well, and you get minimal performance difference. So I can't really explain that other than it's a way of adding more parameters into the model, which could be good. But query and key at least should make sense. Yeah, so the question is, these projection matrices, WQ, WK, WV, those initially are randomly initialized, and then they're learned through backpropagation, so they're parameters of the network. They're very crucial parameters of the network. Other questions?
At what point, while implementing this, do you calculate the loss and perform the outcome?
Yeah, we'll get to that later.
So right now, how we have set up is that the model can kind of query for information that's in the prefix.
Right.
What if it thinks that the next word, some outside information that is not in the prefix would become one?
Yeah, that's a good question.
Set up a database that has
Yes.
queries and then.
So the question is, right now the keys only come from the prefix, but there's certainly information that could be useful generally, like maybe Wikipedia or any other knowledge source. Could the model attend over those as well? Yes, definitely. This is a very important area of research. We'll have a whole lecture on models that are kind of augmented with, their data stores are augmented with a lot of different information that can help them generate the next word. All right, let me check the YouTube comments. Are query key value weights shared? No, they are not shared. They are separate weight matrices. All right, back to what we were doing. Is there another question? Yeah. So the question is, can we look at the words that come after the word that we're trying to predict? So in a language model, no, because that breaks the chain rule, right? We won't be able to generate words if we're conditioning on words that occurred in the future. In other forms, like specifically masked language modeling, where we'll talk about this in a later lecture, yes, you definitely can attend over words in the future as well. So when the key vectors are coming from the prefix, how is it different than an RNN model? Oh, we'll see that at the end of this. So let me just get through this and then I'll take more questions. So you can all obviously imagine how this works for the first position of the sequence as well. You put 100% of the probability on the very first value vector, so nothing special happens. So the important thing here, going to your question, is that now there's no dependencies between H1, H2, and H3, right? All of these are just functions of these queries and keys, but H sub 3 does not directly depend on H sub 2. In fact, those two are not related at all, right? So how can we take advantage of this fact? Specifically, how can we compute H sub I in parallel? So let's just redraw all of our queries and keys. Oops, I used blue for query. This is my Q1, Q2, Q3. And let's forget about the value vectors for now. So we have K1, K2, and K3. So the attention scores that we would like to get for every position are A1 equals Q1, K1. Of course, this is just 1. So when we apply the softmax, this becomes 1. A2 equals Q2, K1, Q2, K2. A3 equals Q3, K1, Q3, K2, Q3, K3. So we're just ignoring the softmax. These are all the dot products we need to compute for every position. So now think about what happens if I group all of my query vectors into a matrix. I group all my key vectors into a matrix, and then take a matrix product. What do I actually get out of this? So specifically, I can make a 3 by whatever the dimensionality of the queries are, where each row corresponds to Q1, Q2, Q3. And I can multiply this by the key matrix, like the transpose of the key matrix, where the columns here contain each of the keys. So what happens if I do this? I basically compute all of the dot products that I want in parallel in one matrix multiplication. So I'll get a 3 by 3 matrix here, where these are just, each element of this matrix is one of the dot products that I actually want to compute, right? So all of these are dot products. So now, maybe I will copy over this thing here. Let's take a look at how this relates to the attention scores that we want to compute. Specifically, our first attention score, we just want Q1, K1, right? So we want this, and we don't want these two. In the second attention score computation, we want Q2, K1, we want Q2, K2, we don't want this. And in the third computation, we want all of these. So if we had some way, and so we're going to remove these, if we have some way of removing these entries in this matrix that we don't want before we apply the softmax, then we've computed all of these attention scores in parallel, right? Which would be great. We computed them using matrix product, which is very efficient on a GPU. So these cells contain info about future words need to exclude. Okay. So basically, I hope I can still paste this. Yes. What we're going to do before applying the softmax on each of the rows of this matrix is we're going to multiply it element-wise by a mask matrix. So this mask matrix is going to be 1 wherever we want to keep the value. So that's here, right? All of these should be preserved. And in the other cells which we want to mask, we're going to set this mask matrix equal to negative infinity. So we're setting it equal to negative infinity because after we compute the softmax, all of the values that are negative infinity will get set to 0. So we'll get the distribution that we want. So in the end, when we do this, I will just paste this thing for the last time. We're going to get a matrix where all of these cells are 0 and the rest, and each row is a probability distribution because we've applied the softmax. I should say, maybe I'll make it more clear, softmax of this whole thing, and the softmax is applied row-wise, so each row is considered a different dimension. Okay, so we got to this point. Now, how can we use this to compute all of the H1, H2, H3 in parallel? It's pretty straightforward. All I have to do is take the matrix product between this thing and our, what color did I use for these value vectors? Purple. And our value vectors. So this is V1, V2, V3. So when I take this product, I get the value weighted average. Essentially, this equals a new matrix, H1, H2, H3. So each row of this resulting matrix contains the value weighted average that I actually want to get. So this, what we've just looked at in the last few minutes here, is why we can get away from the recurrent dependency here, because now we parallelize the attention scores, and then we can do all these computations in just a few matrix multiplications. So I've computed H1, H2, H3, all in just one operation, essentially, like one batch matrix multiplication. There's no dependencies between H1, H2, and H3, which allows me to do this. So this is the basis of self-attention. We'll see in the next class how we can actually use this to build a complex neural network language model called the transformer. So there are things like position embeddings, as you mentioned. So before we compute these value query and key projections, we generally will add a position embedding to each word embedding. So this could be P1, P2, P3, where these depend on what position of the sequence you're at. So why would we want to do this? Because otherwise, we have no idea about the order of the words, right? None of the computations that we talked about so far have anything to do with the order of the words in the sequence. In a recurrent neural network, you naturally get the order of the words modeled because you're going from left to right. Here, you're doing everything in parallel, so you can't really do that. And you need to add these explicit position embeddings in order to get the model to consider the position of words in a sequence. Okay, so right, in the next class we will talk in detail about the transformer architecture. Hopefully this all made sense. Are there any questions? What is the significance of self-attention? So the main thing that we emphasized in this particular lecture is that in self-attention, I can compute all of the representations at every time step in parallel. In a recurrent neural network, I had to compute them sequentially. So when I start training this model over bigger data with many more model parameters, this becomes much more efficient to train compared to the recurrent neural network.
So while calculating the attention, I cannot skip the current key and just take the previous one.
Yeah, so when calculating self-attention, you don't skip the current key. You include that. The current value vector is always included in the weighted average for that time step.
Does this work for only fixed sentences, like we have to when we get to only calculated?
Will this work only for fixed sentences? You mean fixed length sentences? Oh, yeah, so this depends on the fact that you know all of the words in the sequence ahead of time. So if you're somehow adding new words incrementally, you probably should use a recurrent neural network.
When you're creating this, again, this entire thing will happen for a Minibatch. That was it.
Yes, that's a great question. So when we're doing these equations, all of the computations will happen in parallel for every single position in every sequence in the Minibatch. So these matrix operations become tensor operations. We may or may not look at that, but you will certainly have to deal with those in your projects if you're using any of these methods. All right. Why self-attention so powerful? Why is it called self-attention? So here we are, if we have a sequence, the attention is performed. The terminology will make more sense when we talk about sequence-to-sequence models, which we'll do later on. But here, the attention is performed over the sequence that you're trying to predict itself. In the paper, you had to read, for example, there were two sequences, the source language sequence and the target language sequence. Attention was performed on the source. So this terminology is referring to the fact that the attention is being performed on the same sequence that you're predicting on.
Why we use this data structure like three-dimensional parameters as that about to introduce the attention model into our system model?
Sorry, why do we use?
Like, I want to know why we use the data structure like this. Like we use Q, K, and V. There's a reason why we do it to put the attention part into the model, or it's some other reason.
Yeah, the query, key, and value are you can't compute the attention without at least queries and keys. And if the query and key were the same, then you probably, if you imagine like, all your vectors were normalized, you would give a very high score to the current position and always, right? So if you have different query and key for each position, then you're able to score other positions higher than the current position. So all of these are used to compute attention. Yeah.
Another question, is there this relationship between this model and the past model?
The recurrent model? So what is the relationship between this and the previous model?
Yeah, I mean the F1 is the F1 prime.
Oh, I see what you mean. So here, this is just a starting point for the new model that we'll talk about in the next class, which is different than the recurrent neural network. So this is separate. We're moving away from attention in the RNN to a new model, which we'll get to in the next lecture. Yeah, it'll be more clear on Monday. All right, you can come up after class and ask your question. Have a good weekend.